We started talking about reciprocal functions, and we said all reciprocal functions have asymptotes. So in the last video, we talked about vertical asymptotes, and then we also said, okay, well, some of these will have holes. And here what we're really doing is we're talking about the domain of our function. So the domain of our function is what x values will prevent our function from being undefined. So we look at the denominator and we say, okay, well, when is the denominator going to equal 0? And if the denominator is going to equal 0, we have a vertical asymptote, or in some cases we have holes. And we found holes, or we also refer to them as discontinuities, when we factored our reciprocal function and one of those factors canceled out. Then we have a hole. So then we have certain values that don't appear in our range, our y values. So if you remember, we talked about some reciprocal functions that have horizontal asymptotes. So if we go back here to y equals 1 over x, or f of x equals 1 over x, then we see that that y equals 0 is one of those horizontal asymptotes, okay? We're also, for y over x, for f of x equals 1 over x squared, we also have y equals 0 as one of our horizontal asymptotes. So now the question becomes, okay, well, how do we find these horizontal asymptotes? So that's what we're going to work on today, horizontal asymptotes. So to find these, what we're doing is we're asking what happens to y as x approaches negative infinity, and what happens to y as x approaches positive infinity. And there are going to be some places where we're not going to have a y value, right? Because a horizontal asymptote is where our y values approach that line, but they never actually reach that line. And at a horizontal asymptote, our x values always approach infinity or negative infinity. That's always going to be the case. Again, let's go back to that diagram of f of x equals 1 over x. And you can see that at y equals 0, on one side, our x values are approaching infinity. On the other side, our x values are approaching negative infinity. And that's true over here too. Our x is approaching infinity, our x is approaching negative infinity. And when that happens, that is telling us that we have a horizontal asymptote, okay? Because of that, we can never have more than one. And the reason for that is that we would not have a function, right? We can't have a function with more than one horizontal asymptote, because then we have two places where our x is approaching positive and negative infinity, and that would make this no longer a function, okay? So let's just write that down as well. So there can be no more than one horizontal asymptote because otherwise it wouldn't be a function. Okay, so there are 3 different cases of horizontal asymptotes. So again, what we're doing is we're saying, what happens to y as x gets very large? So we're going to keep asking that question over and over again, and you're going to see what happens, okay? So let's take our first case. Let's say that we have f of x equals 1 over x. Now remember our question. Our question is, what happens to f of x as x gets very large? That's our big question. So suppose that we have 1 over a really, really large number. Okay? So 1 over a really large number is very close to 0. It's not 0, but it's very, very close to 0. If we have 1 cookie and we decide to break it up into, what do we have here? 100 million pieces, right? And we take this cookie and we divide it into 110 million pieces. Here we have. Then every person is going to get a really infinitesimal piece of cookie. So it's almost nothing, but it's not nothing. Okay, so that's what we mean by an asymptote. We get really, really close to nothing, but it's not quite nothing. So here our horizontal asymptote is at y equals 0. Because as our x gets very, very large, we plugged in a really, really large number, our y is getting closer and closer to 0. Okay, so at 1 over x, our horizontal asymptote is at y equals 0. Let's do the same thing, but this time let's do it with 1 over x squared. So in this case, we still have 1 over some really, really large number. Again, you take 1 cookie and you divide it into a lot of pieces. It's almost as if each person gets nothing, almost. Okay, you're getting an infinitesimal crumb, but we can't say that you're getting nothing. You're not. You're getting something. So again, it's very close to 0. We're approaching 0, but it's not 0. So once again, the horizontal asymptote is at y equals 0. Okay, let's take another instance that's kind of similar. Okay, let's say that we have f of x is equal to x over x cubed. Okay, well, x over x cubed is the same thing as 1 over x squared. We could take 1x from the top and 1x from the bottom. And we already know that this is 1 over a very large number. Which is close to 0. So once again, the horizontal asymptote, which I'm going to start abbreviating as HA. Okay, let's take one last example. Let's say that we have f of x is equal to x squared plus 1 over x cubed plus 2x. Okay, well, this seems like it's more complicated, but it's actually not. Because if you have some really large number squared and you add 1 to it, you're really not making any difference in that number. So picture you have a billionaire and you hand him $1. Now, most billionaires would say, okay, well, that dollar really isn't going to make a difference in my bank account, okay? If you have a billionaire and you give him even $200 million, it's still not making all that much of a difference in his bank account. I'm sorry, I don't know why this happened here. It's still not making such a big difference in his bank account. So what we can actually say is, let's ignore this, because it's not actually doing much. So this x squared plus 1 over x cubed is essentially the same as, it's not equal. Notice I did not put an equal sign here. It's essentially the same as x squared over x cubed, which we already know is 1 over x. 1 over a very large number is a horizontal asymptote at y equals 0. So in fact, what we're doing is we're saying, what's growing faster, okay? Is the numerator growing faster or is the denominator growing faster? And here the denominator is growing really, really quickly, right? We have 1 and then we have this huge number. If that's the case, then we're always going to have 1 over a very large number, and our horizontal asymptote is always going to be at y equals 0, okay? So let's just write that down. So in this case, the plus 1 in the numerator and the plus 2x in the denominator are insignificant. Compared to the x squared and x cubed. So we can ignore them. Which means that we have our first case. And our first case is the denominator is growing faster than the numerator. How do we know if the denominator is growing faster than the numerator? the degree of the denominator is greater than the degree of the numerator. You look at the exponents. I don't know what happened here, sorry. So if the degree of the denominator is greater than the degree of the numerator, the denominator is growing faster, which means that we have 1 over a very large number because that x over x cubed became a 1 over x squared. That x squared over x cubed became a 1 over x. And 1 over a very large number gives us a horizontal asymptote at y equals 0. That's case 1. Okay, let's look at the second case. Case 2. So case 2 kind of seems obvious. Case 1 is that the numerator is growing more slowly than the denominator, or the denominator is growing faster than the numerator. Second case is the opposite. So let's take simple one. Let's say that we have f of x is equal to x. So again, we're saying what happens to y and y is the same thing as f of x. Okay, well, if we were to plug in a really, really large number, then our answer is going to be a really, really large number. So essentially what happens is that y doesn't approach any number, right? Y gets really, really large. So if y doesn't approach any number, and the definition of an asymptote is a value that we approach but don't reach, then there is no horizontal asymptote. Okay, so as x gets very large, so does y. Which means that there is no number that we approach and therefore no horizontal asymptote. Let's take another example of a function. Let's say that we have f of x is equal to x cubed over x. Well, here, x cubed over x simplifies to x squared. This is actually equal to x squared. And here, as x approaches infinity, so does y. So there is no horizontal asymptote once again. Okay, the idea of a horizontal asymptote is that our y values are approaching a number. If they're not approaching anything, then there is no horizontal asymptote. Let's take one more example. Let's say that we had f of x is equal to 2x to the fifth minus 20x to the fourth plus 6x cubed minus 4 over 3x to the fourth minus 2x cubed plus 23x squared plus 8. Now, once again, this seems like, oh, this is so complicated because there's so much written here. And that's actually not true, because the 20x to the fourth is insignificant compared to the 2x to the fifth. We're talking about exponential growth here. Exponential growth is really, really high. It goes very, very quickly, okay? X to the fifth is much larger than x to the fourth. X to the fourth is much larger than x cubed. So the only values that wind up being significant are the ones with the highest powers. Everything else is insignificant here. It's not really going to change the values. Okay? If you plug in a really large number for x, then the 20x to the fourth, subtracting that, it's not going to make that much of a difference to the 2x to the fifth. You would think it would, but it actually doesn't, okay? So this value here, this function, it's not equal to, but it acts the same way as 2x to the fifth over 3x to the fourth, okay? The only terms that matter are the ones with the highest power. Because the others are so much smaller. That they are insignificant. They're not making enough of a change. Again, if you go up to a billionaire and you hand him $1, most of them are going to say, thanks, but feel free to keep it. Okay. Now, why is this a big thing? Well, if we simplified this, this simplifies to 2x over 3, which means that we have a very large number over 3. Well, a very large number over 3 is still a very large number. So this is no horizontal asymptote. Okay. 2 times infinity over 3, or 2 times the billion over 3 is still huge. 2 times a trillion over 3 is huge. We're getting closer and closer to infinity. So there is no horizontal asymptote here. Which brings us to our rule, okay? Our second case. If the degree of the numerator let's talk about the growth first. If the numerator is growing faster than the denominator, which is the same thing as saying the degree of the numerator is greater than the degree of the denominator, the highest exponent. So we just flip this. There is no horizontal asymptote. So that's the second case. Now we have one more case. So we're talking about the degree of the denominator being greater than the numerator, the degree of the numerator being greater than the degree of the denominator, and then of course we have the case where they're equal. They're growing at equal rates. And that's our third case. So let's start with something like f of x is equal to x over 2x. Okay, well this simplifies. Simplifies to 1 over 2. The x's cancel. So here, as x gets very large, it actually has no effect on our y because there is no x to plug in. Our y is 1/2. Whether we plug in x equals 1 billion or x equals 2, the x's cancel. So we're left with 1/2. And that means our horizontal asymptote is at y equals 1/2. Notice that I never say horizontal asymptote is at 1/2. We always say the horizontal asymptote is at y equals 1/2 because our horizontal asymptote is a line. Okay. Let's take another example. Let's say that we have f of x is equal to 5x over 7x. Well, once again, it doesn't really matter what our x is because our x is canceling. No matter what, our y is 5 over 7. We could plug in any number for x, and our y will be 5 over 7. So our horizontal asymptote is at y equals 5 over 7. Now this isn't just true if we have an x. Let's take the case of f of x equals 3x squared over 12x squared. Well, now the x squared goes away and we just have 3 over 12, or always reduce your fractions, 1 over 4. So our horizontal asymptote is at y equals 1 over 4. Because once again, it doesn't matter what we plug in for x. Our y will always be 1 over 4. And let's take one more instance where we have those extra pieces added in. Let's take f of x is 7x to the 4th plus 8x squared minus 10x plus 3 over negative 6x to the 4th minus 2x cubed plus 70x. And once again, the only terms that matter are the ones with the highest powers because everything else is insignificant. So this 8x squared minus 10x plus 3 is insignificant. This 2x cubed plus 70x, insignificant. The only significant terms are the ones with the highest power. So once again, this is the horizontal asymptote is going to be equivalent to the horizontal asymptote for the function 7x to the fourth over negative 6x to the fourth. It is not that these functions are the same. They're not, right? They are not the same. You get different numbers. If I plug in 1, I get a different number. But their asymptotes are going to be in the same place. So that's why I use the arrow instead of the equal sign. And we know that this is 7 over negative 6 because the x to the fourth goes away. So our horizontal asymptote is that y equals negative 7 over 6. Which means we have our last case. If the numerator and denominator are growing at the same rate, meaning the degrees are the same, remember, the degree is the highest exponent. The horizontal asymptote is the ratio of the leading coefficients. Meaning y equals the leading coefficient of the numerator over the leading coefficient of the denominator. Okay, and that's because the x's, because they're growing at the same rate, they're always going to cancel. You're going to have x to the fourth over x to the fourth. It cancels out. X to the 10th over x to the 10th, it will cancel. The only thing that you'll have left are the coefficients. Okay, so that's the third case. So we have 3 instances. Either the denominator is going faster than the numerator, in which case you have a horizontal asymptote at y equals 0. The numerator is growing faster than the denominator, in which case you don't have any horizontal asymptotes. Or the numerator is growing at the same rate, in which case your horizontal asymptote is at the ratio of those leading coefficients. Okay, so those are horizontal asymptotes. There's one other kind of asymptote that we could have, and that's called a slant asymptote or an oblique asymptote. Okay, slant and oblique are the same thing. So let's talk about that for a second. And I'll show you an example of a function where you have a slant asymptote. So we have vertical asymptotes, vertical lines, horizontal asymptote, horizontal line, or slant or oblique asymptote, which is our diagonal line. There are no other asymptotes. We don't have curves that are asymptotes. Okay, so slant or oblique asymptotes. So a couple of things about these. It only exists if the degree of the numerator is 1 more than the degree of the denominator. So if the degrees are different by any other amount, there is no slant asymptote. The other thing is that you can't have both a horizontal asymptote and a slant. So if you see that you have a horizontal, you don't even have to bother looking for a slant because, again, it wouldn't be a function, okay? So it only exists if the degree of the numerator is 1 more than the degree of the denominator. Notice if the degree of the numerator is greater than the degree of the denominator, then we do not have a horizontal asymptote. So we're not breaking any rules that we've created for ourselves. We haven't really created the rule for ourselves. It wouldn't be a function. So you can't have both a horizontal asymptote and a slant asymptote. Because it wouldn't be a function. Okay, so how would you find the slant asymptotes? The way that we find it is using division. So you divide, and the asymptote is y equals the quotient. Okay, so you find the asymptote by dividing, and the slant asymptote is your quotient, not your remainder. Okay, why is this true? So let's just go back a second to when we did division. So when we did division, we said that our dividend over our divisor, which is what a reciprocal function is, right? It's a rational expression, dividend over divisor, is equal to quotient plus a remainder over divisor. Okay, so why is it the quotient? The reason it's the quotient is that when x is very, very large, the remainder over the divisor this approaches 0. Why does it approach 0? Because our remainder, the degree of our remainder, is less than the degree of the divisor. That's how we know that it's a remainder. and the quotient plus 0 is just the quotient. Okay, so what we're saying is, as x gets very large, the dividend over the divisor approaches the quotient. Okay, so that's why we say that the slant asymptote is y equals the quotient, because this is y, right? Dividend over the divisor is y. The dividend over the divisor is equal to the quotient plus the remainder over the divisor. The remainder of over the divisor is 0. It approaches 0 as x gets very large. So y approaches the quotient. This approaches 0. It's not equal to 0. So y is not equal to the quotient. It approaches the quotient, which means that's what the horizontal asymptote is, because it's what it approaches. So let's take an example. Let's say that we have f of x is equal to x squared minus x over x plus 1. So first of all, the degree of the numerator which I'm going to refer to as n from here on out, is equal to 2. Right? The highest power of the numerator is 2. The degree of the denominator is 1. Which I'll refer to as d. So 2 is equal to 1 plus 1. There is a slant asymptote. So we have to keep going. If this were not true, then we would stop and we would say there isn't any. Okay, so now we do division. So x plus 1 is being divided into x squared minus x, and remember, you need a plus 0. You need a placeholder. For anybody who is uncomfortable with what we're doing right now, go back to the long division video, okay? How many times does x go into x squared? It goes in x times x is x squared. Then we multiply this x by x plus 1. So that gives us x squared plus x. Our next step is to subtract. The x squared cancels. Negative x minus x is negative 2x. We're not done. We have to carry down the plus 0. So don't forget about that plus 0 at the end. How many times does x go into negative 2x? Negative 2 times. Distribute. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. This cancels. We're subtracting this whole thing. And you get 0 minus negative 2, which is 2. And you actually don't have to go through and do this subtraction, because the only thing that you care about is the quotient. And once you get to here, the only thing that you're getting is the remainder. Okay, so in this particular case, the slant asymptote, which we'll call SA, is at y equals x minus 2. X minus 2 is our quotient. And just so that you see what this looks like on a graph, let's graph it. So we have x squared minus x divided by x plus 1. And just so that you see what we mean by a slant asymptote, we said our slant asymptote is at x minus 2. You can see here that our graph does approach x minus 2. It gets really close to it as x goes to positive infinity and as x goes to negative infinity. Okay, so this is an example of a reciprocal function with a slant asymptote. Okay, let's take another couple of examples of slant asymptotes. I'll label this 1. Okay, let's do our next one. Let's use f of x is equal to x squared minus x minus 2 over x minus 1. So remember, the first thing that you're going to do is you're going to check, okay, well, what's the degree of the numerator and what's the degree of the denominator? Because let's make sure that one actually exists. So the degree of the numerator, and my suggestion would be pause the video, try this on your own. There's nothing, this doesn't get any more complicated than what we just did. So try it on your own and see if you could figure this one out. So the degree of the numerator is equal to 2, and the degree of the denominator is equal to 1. 2 is equal to 1 plus 1. So we keep going. There is a slant asymptote here. So x minus 1 goes into x squared minus x minus 2. This is already in standard form, so we don't have to worry about any placeholders. How many times does x go into x squared? X times. Distribute the x. X times x minus 1 is x squared minus x. If we subtract this, everything actually cancels, so we get a 0. And then we could carry down a minus 2, and we're done. This is actually the remainder, because the degree of our divisor is greater than the degree of the what we have here. Okay, so our slant asymptote is y is equal to x. This is the quotient here. So that's our slant asymptote. And that's it. That's all that you have to do to find it. Let's take one more example. Let's take f of x is equal to 3x squared plus 1 over x. So remember, pause the video, see if you can do it on your own. But again, the first thing that you need to do is make sure that you actually have a slant asymptote. So the degree of the numerator, once again, is 2. You're going to find that this happens a lot in this class. Obviously, in other classes at higher levels, you might find that the degree of the numerator is 3 and the degree of the denominator is 2. So just be aware of that. The degree of the denominator is 1. 2 is in fact equal to 1 more than the denominator. So there is a slant asymptote. So remember, both the divisor and the dividend should be in standard form. So x becomes x plus 0 so that you have a placeholder for x to the 0. Then we have 3x squared plus 0x plus 1. How many times does x go into 3x squared? 3x times. We distribute the 3x to the x plus 0. We get 3x squared plus 0x. Subtract. Once again, everything cancels and we bring down the 1 and we're done. Okay? The degree of the divisor is greater than what we have down here. The 3x is the quotient. So our slant asymptote is that y equals 3x. Okay, and keep in mind that for each of these three examples, that means there is no horizontal asymptote. If there's a slant asymptote, there is no horizontal asymptote. So you don't have to even bother looking at the, looking to see if there is one, but you can also, like right here, it's not that hard to see. Degree of numerator is greater than the degree of the denominator. Okay, so let's take this and apply everything that we know and do a couple of examples where we're looking at all three at once. Okay. So what we're going to do is we're going to find, that came out weird. Find the vertical asymptote, the holes, and there can be more than one vertical asymptote. That is not going to prevent it from being a function, okay? Because it's not going to violate the vertical line test. Holes, which we also refer to as discontinuities. The horizontal asymptote and the slant asymptote, which remember, it can also be called the oblique asymptote. It just depends on who you're talking to. Same way that a hole could be called a discontinuity. So we're going to do two examples. First one, f of x is equal to 6x cubed minus 7x squared plus 2x minus 4. And we're going to divide this by x minus 5. Okay, we want to find the vertical asymptote or the holes first, okay? Okay. In order to find the vertical asymptote or the holes, we would factor first. The numerator is not factorable. Now, because of that, the x minus 5 can't cancel. But let's say that you didn't know that the numerator wasn't factorable. What can we do? What we're looking for is to see if x minus 5 cancels. I'm sorry, I don't know what just happened here. There we go. What we're looking for is to see whether the x minus 5 cancels. So you can just plug in 5 and see if it's a factor, right? We can use the factor theorem. You can also divide, but factor theorem is much faster, okay? X minus 5 is not factorable, so what we're trying to say is that x minus 5 is not a factor. Okay, so vertical asymptote. That means the vertical asymptote is where the denominator is 0. The denominator is 0 at x equals 5. Notice that the vertical asymptote is x equals because it's a vertical line. We know that it's a vertical asymptote and not a hole because x minus 5 does not cancel. Again, if you're not sure, just plug in x equals 5 and see what happens. See if your numerator is 0. Okay, horizontal asymptote. Well, look at the degrees. The degree of the numerator is 3. The degree of the denominator is 1. 3 is greater than 1. Well, that means that the numerator is growing faster. So if we plug in a really large number, then our y is going to approach infinity. So there is no horizontal asymptote. Let's look at a slant asymptote. Well, we need the degree of the numerator to be exactly 1 more than the degree of the denominator. So we're asking ourselves, is 3 equal to 1 plus 1? And it's not. There is no slant asymptote here. And that would be it. That's all that you would have to do here. Okay, let's take one more example. And this next one, again, both of these are very typical of problems that you might get on a quiz. Okay. So here, let's say that we had f of x is equal to 2x squared plus 5x minus 3 over x squared plus 7x plus 12. Now keep in mind, in order to find the vertical asymptotes and the discontinuities, we have to factor. So you have to factor everything. I'm not going to go over factoring. Watch the factoring video. 2x minus 1 times x plus 3, that's what the numerator factors to. The denominator factors to x plus 4 times x plus 3. And you might just have to try factoring, okay? With quadratics, it's likely factorable, not always. It's likely factorable. Keep in mind that if it's not factorable, that does not mean that you have no vertical asymptotes. And I'll explain that in a second. It means that you won't have holes because you can't have a factor that cancels if it's not factorable. Okay, so what does this mean? Well, notice that the x plus 3 cancels. So you're going to have a hole at x equals negative 3. Why do we have a hole at x equals negative 3? X plus 3 is in the denominator. So x equals negative 3 would make the denominator 0. But x plus 3 cancels. So it is a hole and not an asymptote. Okay, notice we still are left with something in the denominator. We're left with an x plus 4. So at x equals negative 4, we have a vertical asymptote. X plus 4 doesn't cancel. And x equals negative 4 is going to make that denominator 0. Negative 4 plus 4 is 0. Okay, horizontal asymptote. Let's look at the degrees. The degree of the numerator is equal to 2. Remember, highest power. the degree of the denominator is also equal to 2. So we're going to look at the ratio of the leading coefficients. We're going to look at the leading coefficient of the numerator over the leading coefficient of the denominator, because they're growing at the same rate. And if we're growing at the same rate, then we're looking at the ratio of the leading coefficients. Remember, that means that the 5x minus 3 can be ignored. The 7x plus 12 can be ignored because they're insignificant, which means that the x squared would cancel, and we would have y equals 2 over 1, or 2. Technically, we don't have to go any further. The slant asymptote we already know can't exist because there's a horizontal asymptote. So we can look at 2 reasons here. If there's a horizontal asymptote, there is no slant asymptote. So you don't even have to go any further. But we can also say the degree of the numerator is not 1 plus the degree of the denominator. So we have 2 reasons here, which clearly, and you would never have one where there's a horizontal asymptote and then have this be the case where the degree of the numerator is 1 plus the degree of the denominator. Okay, so there is no slant asymptote here. And that's it. So you should be able to find poles, vertical asymptotes. Oh, and I said if it's not factorable, there still could be a vertical asymptote. The only time that there wouldn't be a vertical asymptote is if you use the quadratic formula to figure out where this is equal to 0 and you got imaginary numbers. If you get a real number, then there is a vertical asymptote. Okay, so let's just write that down. There is no vertical asymptote if the denominator can't be 0. For example, if your denominator is quadratic, and the quadratic formula gives you imaginary numbers. If the denominator is not factorable, you can still have a vertical asymptote. That's because we have a lot of, and I use quadratics because you're familiar with that. We have a lot of quadratics that are not factorable, but they do give us real roots. Okay, so I just wanted to make a note of that because that does come up, I think, in one of the homework problems even. Okay, and that's it for asymptotes, and that's it for reciprocal functions.